All right. Question 8. Let's see here. An earthquake is traveling from west to east through rock. If the particles are vibrating in a north-south direction, the wave must be classified as which of the following? So we have an earthquake traveling from west to east. The particles are vibrating north and south. What kind of wave is this? Well, we see the wave is traveling one direction, the particles are traveling perpendicular to. So perpendicular waves are the transverse kind. All right, a longitudinal wave would be something like the wave is traveling from west to east and the particles are traveling back and forth like this. That would be parallel, which is longitudinal. So the diagram below shows a transverse wave moving to the right along a rope. As the wave passes point X, the motion of X will be, all right, so as this wave is moving, the first part that's going to reach X is this chunk here. As this chunk reaches X first, X is going to move down, right? It's going to move down. And then this chunk is going to reach, and then X is going to move up, and then X will move back down. So X is going to go down first, then up, then down. So it should be down and up. 10. A wave travels through a medium. The particles of the medium vibrate in the direction of the wave's travel. Which type of wave is traveling through this medium? So the particles are vibrating in the same direction the wave is traveling. That's like this example up here. The wave is traveling one direction, the particles are vibrating back and forth in that same direction. That's parallel. Parallel is longitudinal. What is the velocity of a wave having a frequency of 25 cycles per second? So that's going to be my F. And a wavelength of 10 meters. And you're looking for V. V equals F wavelength. V equals 25 times 10. 250 meters per second. If the period of a wave is doubled, its wavelength will... So I think this is one of the more tricky questions that I gave you guys. If the period of a wave is doubled, its wavelength will what? So we know that period equals 1 over frequency. By the same token, frequency equals 1 over the period. So if you double the period... it's going to decrease the frequency, right? It's going to decrease the frequency by half. So doubling the period reduces the frequency by half. So if you have this equation, and now you have half the frequency, so if you only have half the frequency, now the speed is going to stay the same. What's going to have to happen to the wavelength? Well, you will have to have doubled the wavelength in order to keep the speed the same. And we've talked about this a couple times, right? If you have a low frequency, that would be like a few amount of waves. That's like a low frequency. Long wavelength, low frequency, long wavelength. High frequency, short wavelength. The waves are short, and there's many of them. So what was it? Doubled. 12. 13. What is the wavelength of a 30 hertz? You see this word hertz? You should know that we're talking about frequency. All right, that's from your notes. 30 hertz periodic wave moving at 60 meters per second. 60 meters per second, that's a speed. So they've given us the V equals 60. The F is 30. And they're looking for the wavelength. V equals F times wavelength. 60 equals 30 times the wavelength. Divided side by 30. And we get the wavelength should be equal to 2. And this is the length, so this is going to be meters. 2 meters. All right, 14. As a wave travels between 2 points in a medium, the wave transfers energy and mass, or neither energy, mass. Well, we talked about this in class, how matter can only occupy one place at a time, right? Multiple things of matter can't occupy the same place, but waves are not matter. They're energy. It's a transfer of energy. It's a transfer of information. So waves transfer energy only. They don't transfer mass. All right, that's why when you have an ocean wave, and there's a wave coming at you, all that's happening is the water is moving up and then down. It's not the actual water from this chunk of the ocean coming over to the beach. The water from this chunk of the ocean is staying there. It's just moving up and then down. It's really the water that's at the shore that's crashing on the beach. So let's open the next chunk. So let's resize that. All right. A series of pulses generated at a regular time intervals in elastic medium will produce. So a couple of pulses are producing what? Antinodes and nodes? Nope, those are standing waves only. We never talked about polarized waves, so it's got to be periodic wave. Periodic wave just means a wave that's happening over and over. The diagram below shows two pulses, A and B, moving to the right along a uniform rope. Compared to the pulse A, pulse B has a greater amplitude. We see that here. So if it has a greater amplitude, it has more energy. So we'll get rid of these less energy ones. And it's either a slower speed or the same speed. Well, in the Slinky, we all saw that the speed of a wave is constant, regardless if it had a lot of energy or a little amount. Right? The speed in a medium is always the same. That's why the speed of sound in air is always the speed of sound in air. There's nothing you can do to make sound travel faster in air. Just because you talk louder doesn't mean it's going to travel faster. So the same speed. Speed is only different if it's like a different medium, like we're talking about water or something else. Two pulses below are approaching each other in a uniform medium. One's 5, one's 10. Which diagram represents the superposition? Well, we know that in this case it's going to be constructive because they're both in the same phase, right? They're both displacing upwards. So 5 plus 10 is going to be 15. Nice and simple.